Welcome to the video tutorial for the Unit 12 take-home test. We are almost done. Alright, as always, anything you see highlighted in green is something I'm not going to do. I'm going to leave blank for you to do on your own. Something you see in yellow is something that I'm still going to do on the video. Go ahead and check your answers for number 1. Okay, it's there. Push pause if you need more time on it. Looking down here for these ones, you've got your symbols and your definitions. These are things to memorize. It's a very memorization heavy. So if you don't feel comfortable having these memorized yet, please make sure you're making flashcards or doing something to get those definitions and ions memorized. Looking here, when we talk about Arrhenius, students kind of freak out. Arrhenius is the rules that we always use in class. And we always say that acids start with H. That's the Arrhenius definition of an acid. And that base is in an OH. That's the Arrhenius definition there. Okay. Looking down here at the rest of the page. Okay, go ahead and check your answer, see what you're doing. I want to look at number 11 together, though. For number 11, I drew up a number line on the pH scale, saying that 0 is acidic, 7 is neutral, and, oh wow, I put 9. That's true, it's a base, but I probably should have just put 14 there. 14 is a base. Okay, so solution A, we're going to start at a pH of 2. We're going to start right here, and it says we mix it with solution B. The new combined pH is a 9. So whatever solution B was, it pushed us all the way over here to a pH of 9. So it's asking, what did we add to it? Well, if we went this direction, we got more basic, which means I must have added a base to it. And adding a base means I added a lot of hydroxide ions to the solution. Initially we were acidic, so I had more H+, and then we eventually got neutral, and now we have more OH. So it pushed us towards the basic end of the spectrum. That's page 1. Go ahead and pause or rewind, whatever you need. For page 2. Page 2, I've got some extra credit for you, if you're listening. Okay? If you draw this up, you get 3 extra credit points. Okay? Acids always start with H, according to our Arrhenius definition we use in class. So H ... is how you know it's an acid. ... OH, so ending in hydroxide is how you know it's a base. You would know that something is a salt if it's a metal plus a nonmetal, or a metal plus a polyatomic. That means it's an ionic compound. And all 3 of these are considered electrolytes. So go ahead and write 3 extra credit points if you copy all that down. Using those rules, then, that's how you're going to complete the table, telling if it's an acid, base, or salt. So I've already done some of it for you. You can check your answers. I want to finish up by looking at the names here for these 2 acids. So we've got H3P and C2H3O2. And there are missing parentheses there because there's an invisible one. They're invisible. All right. But the difference between these 2 acids is that this one is an oxy acid because it has oxygen, and this one's not. It's a binary acid, or what we call a hydro acid. So if there's only 2 elements, you're going to call it hydro-blank-ic acid. In this case, it's phosphorus. So we're going to say hydro. Instead of phosphorus, we call it phosphic or phosphoric. Remember, those are extra letters, phosphoric and sulfuric. They get extra letters. And you have to make sure you say acid. Okay, hydrophosphoric acid. Because this is an oxy acid, it is not a hydro acid. So I will not call this one hydro. I'm just going to call it acetate. Acetate, whoops, I spelled that wrong. Acetate acid. But instead of ate at the end, I'm going to say I ate too much, so I feel icky now. We're going to call it acetic or acetic acid. If you said hydroacetic acid, you'd be wrong. If it's an oxyacid, it's not a hydroacid. Alright, so let's look at some of the formula writing. I started some of the work on J for you, but I want to go through these 3. Sulfurous, sulfuric, and hydrosulfuric. Remember, almost right is wrong when it comes to formula writing. So they look similar, but they're not. They're all acids. So they all start with H plus 1, because acids, again, according to the Arrhenius definition, always start with H. And then sulfurous, sulfuric, and hydrosulfuric. Let's start with this one, this hydrosulfuric. It's kind of what we're looking at up here. If it's a hydro acid, that means it's not an oxyacid. which means if it says hydro, we're not using polyatomics. Okay? If it says hydro in the name, we're not allowed to have oxygen, which means I'm not allowed to use any of these. I'm just going to use the periodic table. So hydrosulfuric is just sulfur, hydrogen and then sulfur. And sulfur in family 6A needs 2 more electrons to be like family 8A. So it will always gain 2 more negatives. It'll be a negative 2. Then we crisscross H2, S invisible 1. And when I rewrite my final answer, for hydrosulfuric acid, it should be H2S. For just regular sulfuric acid, it doesn't say hydro. So if it's not a hydro acid, that means it has to be an oxy acid. So I'm going to need to have an oxygen in it, which means it's going to be one of these 2 things. So sulfuric acid. I feel icky if I ate too much. Sulfuric is hydrogen followed by a sulfate, SO4 minus 2. So I'm going to go ahead and write down sulfuric sulfate, making a negative 2 charge, which we then crisscross the 1 there. My final answer should be H2SO4. If you want to leave in the parentheses around SO4, you can. They're invisible and they will be on the test, but you're allowed to leave them if you get more comfortable with it. Sulfurous acid, again, is going to have a polyatomic. It's an oxy acid because it doesn't say hydro. But delicious are bites, I-T-E. Remember, bites are delicious. So this used to be sulfite, which is SO3. It's still a negative 2 charge, so we still crisscross the 1 and the 2. H2SO3. So they're all similar, but almost right is wrong. They are very different acids in real life as well. Okay. So check your answers, see how you're doing. If you're struggling on this, go back and watch the video tutorials from day 1 and day 2 homework. Looking down here at some of these ones, okay, I put up a number line for you to help you with 14 and 15. It says if there are slightly less, if you have exactly equal hydrogen and hydroxide ions, then it's a pH of 7, it'd be water. If you have just a little bit more of H+, you're just a little bit more acidic, which means you're still pretty close to neutral, but you're acidic, which would be a pH of 6. This one, pH of 1, is very acidic, so I would have much more of this compared to this. If I was just a little bit basic, that's what we'd look at. So looking down at this one, if there's significantly more hydrogen ions compared to hydroxide ions, then it's significantly acidic, which would be closer to 0. All right. The reason I knew that this was a weak electrolyte, or excuse me, a weak acid, which is a weak electrolyte, is because some of the acids are still stuck together. Not all of them came apart. Only 2 out of the 6 came apart, which means it's not a strong acid, it's a weak acid. Got some more extra credit here. So here's points 4 and 5. Acids will either turn litmus paper red or keep litmus paper red. Bases will either turn blue or stay blue. So go ahead and write this down, box it in, and put 2 extra credit points there. And that's the information you're going to use to answer these ones. Okay? And I put some hints there. So push pause and work on this. Looking over at page 3. Okay. Remember, acids are closer to pH of 0. So a solution becomes more acidic as the pH is lowered. If you raise the pH, that means you're getting closer to 14. Okay, I've got some of these answers filled in when it comes to predicting products and naming. And then the green ones I want you to try on your own. We're going to work on number 26 together because that's got the least filled in to start with. So the first thing I'm going to do is write the formulas here. Phosphoric acid. If it's an acid, I know it starts with H+1. Phosphoric. I know that this isn't phosphorus because that would be hydrophosphoric if it was phosphorus. If it doesn't say hydro, then it must be an oxy acid. So it's either going to be phosphate or phosphite. And remember it says phosphic. So if I ate too much, I'd feel icky, which means it's going to be PO4 is my thing after hydrogen. So I'm going to go PO4, making a negative 3 charge and crisscross. H3, PO4. That's the symbol for, the compound or the chemical formula for phosphoric acid. Sodium hydroxide is sodium and hydroxide. Both of them make 1 charges, so we end up with just Na OH, and you can leave it with or without the parentheses. I always like adding them in, so if I was doing this problem, I would add them back in even though they're invisible there. It's easier to see. Okay. Then what I'm going to do is I'm going to take the elements that are in front, and I'm going to keep them in front. So my H was in front, I'm going to keep it in front. My sodium was in front, I'm going to keep it in front. The difference is I'm going to switch the backs. So instead of hydrogen and phosphate, I'm going to have hydrogen and hydroxide. And instead of sodium and hydroxide, I'm going to have sodium and phosphates. Right? We're not done. That's just step one. That's symbols. Then you have to do charges, crisscross, reduce, and erase. Now, these ones are both +1, -1, so it's just HOH. Sodium makes a +1 charge. Phosphate, we already set up here, makes a -3 charge. So when I crisscross it, I'm going to have an invisible 1 behind phosphate and a 3 in front of phosphate. And a 3, PO4, is the symbol for that one. HOH is the same as H2O. It's water. It's just easier to balance it when we write it like that. So when I name it water. And sodium and PO4 is ionic. It's a metal and a nonmetal, in this case a polyatomic, which makes it the salt. So I'm going to go ahead and circle it. And naming things that are ionic is what we've been doing since October in Unit 4. So we just name the metal sodium. Sodium does not get a Roman numeral because it's in family 1. And then PO4, we call it phosphate still. Now, PHATE. It's been making me crazy watching students call it sodium phosphate. And they'll say, why did you call it phosphate? And I said, because if you ate too much, you feel icky. If you ate too much acid, you feel icky. This isn't an acid. So over here, we call phosphate phosphate because it's acidic. Over here, it's not acidic anymore. It's not an acid. Now it's just a salt. So we keep it sodium phosphate. All right. Again, if you need help with this, you need to go look at pages 8 and 9 in the homework packets. There's a video tutorial for that to kind of help you get caught up. Down here, this is more like your day 4 homework, which is pages 6 and 7. I'll go ahead and give you 1 point of extra credit if you write pH plus POH. Always has to equal a total of 14. And then I really like color coding. Some of my students will draw hearts around the acids and box the base. Whatever it is, just slow down and pay attention to details on these ones. So in this case, I know that these are both acids because it's the concentration of H+, which is an acid, and it's pH, which means the concentration of H, the acid. So when they're both acids, I just keep the exponent, 8, but I make it positive instead of negative. So my pH stays 8. My POH, so if I'm going from pink to blue, from acid to base, I say 14 minus 8 equals 6. So that pH plus POH, 6 plus 8 is 14, and I'm good. So acidic, basic, or neutral, I need to look at my pH. If I'm over 7, if I'm big on the pH scale, then I am basic is big. So this would be slightly basic and be a base. If my POH, that means my concentration of hydroxide, it's a base, is 5, what's the pH? So I'm going from a given base value to a pH value, an acid value. So going from blue to pink, I'm going to say 14 minus 5 equals 9. That's what they add up. 5 plus 9 is 14. Using a pH meter, the pH was found to be 3. They're asking me for H+ concentration. That means that they want it to look like this. So I'm going to say 1 times 10 to the negative something. Okay? And they're asking me for the concentration of an acid. They gave me the pH, which is an acid. So going from pink to pink, I keep the number. But instead of making a -8 exponent positive, I'm going to keep the +3 exponent and make it negative. 1 times 10 to the negative third. That would be the concentration of hydroxide ions. Again, if that's a little bit confusing to you, check the homework from day 4, pages 6 and 7. Looking down here, anytime we're talking about acidic, basic, or neutral, you have to compare it on the pH scale. So all of these values need to get put into pH before we can compare them. So in this case, they're giving me concentration of H+. This is an acid value. So the pH of an acid stays just this number, but positive, 8. Here, this is a base value. They're giving me a concentration of hydroxide. So my pH is not 12, right? This is my POH. So in this case, my POH is 12. Whoa, I already wrote that. pOH is 12. So 14 minus 12 equals 2. My pH would be 2. H3O plus hydronium ion is also an acid. So they gave me an acid to an acid. I keep the number. H plus is an acid, so I keep the number. Just make it positive. So comparing now, pH of 8, pH of 2, pH of 12, or pH of 3, the most acidic one would be the one closest to 0, which would be pH of 2, or pOH of 12. Those are the same thing, and they both mean acid. Let's take a look at page 4. Page 4, we're asking you to correct your true and false. Okay? So if you had any false answers, you need to correct them. I showed you all my work. Okay? You didn't have to correct them the exact same way I did, but you do have to correct the false answers. Looking down here for matching, I gave you most of them. I want to look at number 40 together, and then you're going to be in charge of filling in the other blanks. Okay? A Bronsted-Lowry base. Bronsted-Lowry is all about protons. So a Bronsted-Lowry base is either a proton donor or a proton acceptor. And in this case, a proton for a base, it would be proton acceptor, which means we want to look at accepts protons. Proton acceptor. That is the definition for Bronsted-Lowry base. That was on page 1 of this packet as well. Okay, let's take a look down here. This is just like what we were doing at the bottom of page 3. They're asking me for the pH, which means the concentration of hydrogen if they give me this concentration of an acid. So they're both acids, pH and HCl. So I can just keep this number, but instead of to the negative 6, I'm just going to make it positive 6. For number 46, they're giving me H3O+. That's an acid, and they're asking me to turn it into a base, pOH. So I do not want to say that this is 3, because the pH is 3, which means the pOH is 14 minus 3, 11. So that total, they add up to 14. Going from the pH to the concentration is always going to be 1 times 10 to the negative. And if it's pH acid to concentration of H acid, I'm going to keep the number. It's a negative 5th. Circle a solution that's the most basic. That means the highest pH. Okay, the biggest pH is the basic. pH of 1, pOH of 4. That means 14 minus 4 would be pH of 10, pH 7, or pOH 12. 14 minus 12 is 2. So now that I'm in pH, I can compare it 1 versus 10 versus 7 versus 2. My most basic would be pOH 4 or pH 10. That's the biggest value on the pH scale. Number 49, the hydroxide ion concentration. I highlighted this in blue because it's a base. The OH concentration is 1 times 10 to the negative 11th. And that means that this 11 goes to the blue, the OH. The base number goes to the base. And then when I go from blue to pink, it's going to be 14 minus 11 equals 3. So that total, they add up to 14. What is the pOH of a solution of base? So going from base to base, I keep the number and make it positive, so we're going to say 6. And now it's going to ask you if it's an acid or a base. We don't know yet, because we have to talk about acid or base in the pH scale. So if the pOH is 6, 14 minus 6 would be 8, right? And bigger than 7 means that this is a base. I know because pH is over 7. Let's look at page 5. On page 5, I gave you the safety rules and kind of the starting stuff, looking at acid, base, and neutral. We talked about this. We demonstrated it as teachers in class. Please make sure that you're accountable for this information on the test. So push pause, copy it down, think about it. Read this little note here. Okay. Looking down at the bottom then, we want you to balance some neutralization reactions. The first thing you need to know is the typos, right? In your packet it says Mg, and this is listed as C. I copied and pasted, but I forgot to change this one. And then if this is beryllium, this one should also be beryllium instead of barium. I already did number 57 for you, showing the work. I'm going to show you how I do my work on number 56. I always cut mine in half. I'm going to do it in red so it stands out a little bit more from this work. I cut my problems in half and I write down what I have. I have beryllium. I have hydroxide. Okay, I'm going to keep OH together. And then over here, I want to put my invisible parentheses back. So Cr2O7 is dichromate. I want to put that one back in there. I have hydrogen, and I have Cr2O7. I'm going to keep those all together. Then looking on the other side, I want to copy it down in the same order I put on my product side, or excuse me, my reactant side. I was right. Beryllium, hydroxide, hydrogen, and chromate, dichromate, Cr2O7. So I like to tear apart water, H2O. Instead of writing it as H2O, I write it as HOH, so I can see the acid part, and I can balance it with the base part. That way I don't have to balance hydrogen from one spot to two spots. So looking at it initially, I have one beryllium on each side to start with. I have two hydroxides on my reactant side, and I have just an invisible one hydroxide over here. I have two hydrogens, H2, and I have one hydrogen over here, because my other hydrogen I'm counting as an OH hydrogen. And then I have one dichromate and one dichromate on this side. So my berylliums are balanced, my hydroxides are not. So I have two on this side, I have to make this side match it. The smaller side has to match the big side. So 1 times 2 would equal 2. And in order to get hydroxides to be a 2, I have to put a big 2 out front. That makes hydroxide a 2, but it also makes the hydrogen a 2. It changes both of them, which is actually pretty okay with me. It gives me 1 of each beryllium, 2 of each hydroxides, 2 of each hydrogens, 1 of each dichromates, so I'm balanced, and it would just be 1s where everything else is blank. So the molar ratio would be 1 to 1 to 1 to 2, which means I have 2 moles of water for every 1 mole of dichromic acid that reacts. If you need more help on balancing, on my website I posted the rainbow balancing video from Unit 5 that Ms. Hansen made. It's a different technique. It's really helpful. Last but not least, we have some vocab for you. It's a very vocab-heavy unit, right? So take a look. I filled in some of the blanks for you, and I left some of them blank. You should be able to find the remaining ones based on there. You can check your answers and try and figure them out. All right. Great job.